Alright guys, welcome to chapter 7.2, which is looking at electrical current and voltage. So some of the topics we're going to be discussing today are how do we define electric current, what are the macroscopic and microscopic descriptions of electric current, and how do we define electrical power. So definition for electrical current is a flow of electrical charge. In the textbook, it gives the definition as the rate of motion of electric charge carriers from one part of a conductor to another. We use the symbol I to represent current, and it has the units of amps or amperes, which use the um, symbol of a capital A for the units. So the formula for calculating electrical charge is just the rate of flow of electric charge over time. So I equals Q over T. So remember last lesson, chapter 7.1, we looked at electric charge being measured in terms of coulombs. So if we're measuring electric current, we can say that an electric current is measured in terms of the coulombs of charge per second of time flowing around or flowing past a particular point in an electric circuit. So we can define an amp of current as being 1 coulomb per second. And remember from last time we looked at the coulomb of charge is 6.25 by 10 to the 18 electrons. So 1 amp of charge could also be described as 6.25 by 10 to the 18 electrons per second. So just to get an idea about like what actually is an amp, so your lights in your house, 0.25 amps, I think that might be like old incandescent lights. These days, pretty much everyone has LED light bulbs, which would probably draw a lot less than that. When you turn your microwave on, it draws about 3 amps. If you have an electric stove at home, it draws about 15 amps. Your mobile phone chargers usually draw, I think, 2 amps, depending on whether it's got fast charge or super fast charge or whatever. Um, so most like your circuits in your house usually have 10 amp circuit breakers on them. So usually, like I used to have a problem where if we plugged the toaster into the power point on my bench and turned the microwave on at the same time, it would blow that circuit breaker because it was obviously drawing more than 10 amps of current having those two appliances going at the same time. So just a working example, 7.2, which is on page 212 of your textbook. A charge of 30 coulombs passes through a light bulb in 1 minute. What is the current flowing through the bulb? So using the formula I equals Q on T, we have 30 amps divided by 1 minute. So make sure we convert our units into seconds, because remember that an amp of current is measuring the coulombs per second. So we've got 30 coulombs divided by 60 seconds, which means there would be half an amp of current flowing through that light bulb. So please make sure you're really careful with your unit conversions. If you do forget to convert your units of time into seconds, then you're going to be very, very far off the correct answer. 7.2b on the same page, we have a current of 2 amps passing through a light bulb in a torch. Calculate how many coulombs of charge pass through every second and how many electrons pass through it each second. So just rearranging the formula I equals Q on T. So if we know I, we know T, we're trying to work out Q. We have Q equals I times T. We have 2 amps of current times 1 second. So that means that 2 coulombs of charge would have flowed through our torch. And because we are using the formula from last time where we had the number of elementary particles or the number of electrons equals the total charge divided by the charge on a single electron, we have 2 coulombs of charge divided by 1.6 by 10 to the negative 19 coulombs per electron, which means we would have had 1.25 by 10 to the 19 electrons flowing through our torch. Now, it gets a little bit confusing when we start talking about electric current because they discovered electric current before they discovered the electron. They just arbitrarily defined the direction that current flows as the direction that a positive would flow if it was flowing through a circuit. So we always define electric current as the direction that a positive charge would flow around a circuit. So we say that electric charge goes out of the positive or electric current, sorry, comes out of the positive terminal of a battery and flows into the negative terminal. But what actually is happening is we know that electrons are the only things that are free to move around. They're the only things that transfer charge. So our negatively charged electrons are leaving the negative terminal of the battery and flowing into the positive terminal. So we have two types of charge. The first is called conventional current, and the second is called electron flow current. So in all situations, unless you're told otherwise, we always describe current in terms of conventional current, which is the flow of positive charge out of the positive and into the negative of our battery. In only very rare situations, or if we're just trying to assess whether you actually understand how electricity really works, will you ever be asked with electron flow current. So please don't get confused between conventional current, the direction of a positive would flow through the circuit if it was free to do so, with what's actually happening of electron flow current. Okay, so if we have a wire, in which wire are the electrons moving from left to right? So the symbol I in the top one X, the symbol I is always referring to conventional current. So conventional current is flowing from left to right in the top wire, so it's not that one. In the second wire labeled Y, we have electron flow current traveling from left to right. So it's obviously not that one again. In Z, we have conventional current flowing from right to left. Hang on, I've got that wrong. It was in X, wasn't it? In I, positive charge is flowing from left to right, therefore electrons are flowing from right to left. So in X, the first one, the electrons would be flowing from the right-hand end of the wire to the left-hand end, opposite to the direction of conventional current that's illustrated there. So the answer would be in X only, is the electrons moving from right to left. So electric current, we can look at electric current being generated in two different, or look at electric current flowing in two different ways. We can have electric current, which is described as direct current, which is current that only flows in one direction through an electric circuit, or we can have alternating current, or AC current, which flows, the current flows in one direction and then flows in the opposite direction, alternating at a certain frequency through the circuit. So we all know that the power that we get out of our power points, out of the wall, that's in AC current, but the power that gets used by appliances, by your computer, by your phone charger, by your microwave has to be direct current. So the difference between alternating and direct current is direct current only flows in one constant direction around a circuit, whereas alternating current, the direction of current flow swaps from going, say, clockwise around a circuit to then anti-clockwise, back to clockwise, back to anti-clockwise, however many times per second the frequency of that signal is. So if we look at direct current is, oops, sorry, how do I go, can I go back on this? Okay, so my apologies. It seems that I can't go backwards when I'm recording this. So the previous slide, you might just want to rewind the video a little bit and pause on the previous slide. It was just a screen cut from page 213 in your textbook. So if we think about direct current, you can think about it like the water flowing around a pipe which has a pump which is pumping in one direction. So the electric current gets like pumped out of the battery. It flows through some device. In this case, they've got a light bulb there, and then it passes through the ammeter, which measures the rate of current flow on its way back to the battery. And it always flows in that diagram in the clockwise direction, because we've only got like a battery, we can only have direct current coming out of. Whereas if we have an alternating current signal passing through a circuit, so in class when we get back to school, we'll go and do some experiments with our power packs because they have an AC signal generator in them. So we can look at the current would flow rather than having our battery only pushing current in the clockwise direction. The current would initially flow in the clockwise or the positive direction as indicated on the graph here, and then it would switch to the negative direction and then switch back to the positive, back to the negative, back to the positive again. So in the AC circuit, the signal you can see there of current versus time continually swaps from the positive to the negative to the positive again. So positive is just arbitrarily defined as one direction around your circuit, and then negative is just the opposite direction for the current to flow. So hopefully we would all understand that electricity only flows when we have a closed circuit. So if you have an open circuit, or you have something like the diagram here where your switch is open, then no electricity is going to flow through the circuit. So if you want electricity to flow through your electric circuit, you want current to flow through your circuit, it must have a closed circuit or a closed pathway for the electrons to flow out of your battery through whatever object it is that's using the electrical power, and then get back to the battery again. So how do we create electric current? So in order for an electric current to flow, there must be an electric potential difference between 2 points in your circuit. So what that means, you can think about it like water only ever flows downhill. You can never make water go back up the hill. It will only ever flow from the point of high gravitational potential to a point of low gravitational potential as it flows down the circuit, as it flows downhill. The same thing happens with electric current, so it flows from a region of high electric potential to a region of low electric potential. So the two terminals on your battery are actually different electrical potentials. And that causes the electrons to be actually attracted away from the negative terminal of your battery and flow around through the circuit to the positive terminal. Another way of thinking about it is that opposites attract, likes repel, so your negatively charged electrons are repelled away from the negative electric potential of the negative terminal of the battery. They're attracted to the positive electric potential region at the positive terminal of your battery. If we connect those 2 points of different electric potential, so the positive and the negative terminal on your battery, if we have a closed circuit, then we can have electric charge flowing. We'll have an electric current flowing through our circuit. So circuit symbols we'll get up to in chapter 8, I think it is, when we start looking at actual electric circuit diagrams, but just some simple circuit symbols. So the top there, the large line with the small line beside it, that represents a cell or a 1.5 volt battery, and then the zigzag jagged line represents a resistor or some resistive element. So we always have to have some object in our circuit, some resistive element that dissipates the electrical energy. So in the case of the picture there, we've got a light bulb. So the light bulb could be represented as a resistive element. It has some resistance, and that allows it to convert the electrical energy into light and heat energy. If we don't have a resistive element, if you just short circuit your battery, connect a wire directly from the positive to the negative, it'll basically try and dump all of its charge as quickly as possible, and you'll end up overheating the wires, possibly causing a fire, possibly causing the battery to explode. So it's always important to have some resistive element or some element in your circuit that can dissipate the electrical energy that you're passing through it. All right, so super simple question. You've set up this circuit here, but you've forgotten to connect a battery, the battery back to the light bulb. What's going to happen here? Obviously, number one, no current's going to flow because it is an open circuit. So what are the macroscopic versus microscopic properties of electric current? So remember when we were talking about thermodynamics back at the start of the year, we looked at the macroscopic energies versus microscopic energies. So it's kind of the same thing here. Macroscopic are the things that we can observe with our eyes or things that we can see normally, whereas microscopic things that we can't see but are actually occurring. So what's actually happening when you connect a battery into a circuit? So the charges, as you can see here, these little Qs, when we were looking at our temperature topic, our particles are in constant motion. Our battery supplies a potential difference, which creates an electric field, and that's directed in one direction, in this case from left to right. And that electric field causes our particles, our charged particles, to be forced in the direction of the electric field. So then they get accelerated and they start to move through our circuit. However, these particles, they're not just free to move around. They're not just going to move like water flowing through a pipe, because obviously in any material we have other atoms, we have nuclei, we have things that are in physically going to slow down our particles as they move through the wire. So these collisions are what causes resistance. So things that have a low resistance have a low number of collisions when the electrons are flowing through them, whereas things that have a high resistance, they have a large number of collisions that occur as your electrons are trying to pass through them, and that causes the electric current to decrease as they try and flow through there. The topic there about drift velocity, we're not going to go into that in this course. So if we look at the actual movement of electrons, if we could zoom in with a powerful enough microscope and actually chart the course of a single electron as it flowed through a piece of wire, it's not just an electron moving in a straight line. So the electron is going to be repelled away from all of the other electrons that are bound to the copper nuclei. So the electron's going to experience a whole bunch of collisions where it's like bouncing around. Generally, it's flowing from left to right. However, some of the collisions may cause it to go backwards on itself. With a copper wire, though, there would be a low number of collisions, and in general, it would move fairly quickly through that wire. If this was replaced with something like ceramic that most resistors are made out of, or something called nichrome, which is a form of metal, but it's a metal that has a high amount of resistance, we would see a lot more collisions, and the path of our electron passing through that section would be a lot more haphazard, would have a lot more bouncing around inside there as it moved from left to right. So we measure current using an ammeter. An ammeter is just a device that we have to connect in series. So we're going to look at the difference between series and parallel circuits in Chapter 8. But an ammeter is a device that you literally just pass electricity through, and it tells you how many amps by measuring the number of coulombs of electrons per second that are passing through it. We use the circuit symbol of a circle with a capital A in it to denote an ammeter. Now, it doesn't matter where in the series circuit we connect our ammeter, because if you think about this simple series circuit here where we have a single battery with an ammeter and the cross with the circle is a light bulb, the electric current can only flow from talking in terms of conventional current, would flow out of the positive or the long arm of the battery, would flow anti-clockwise around that circuit, passing through the ammeter, then passing through the light bulb before going back to the negative terminal or the shorter line of our battery. So there's no other paths that the electricity can flow, so it doesn't matter if we measure the current before or after the light bulb. Because we're counting how many electrons per second are passing through our ammeter, that's going to be the same at all points in the circuit. So when we're dealing with electric current, we're not like the electrons aren't being taken out of the circuit. We're just taking energy from those electrons to use in our light bulb to create light and heat, but the actual number of electrons that are passing through our circuit remains constant at all points in the circuit. Okay, so you can go and do Check Your Learning Chapter 7.2. That's on page 216 in your textbook. As with last time, you have work assigned to you on Education Perfect and CK12. So please go and have a look at that if you would like to get some more help with this topic or you'd like to do some more review of this topic. Thanks very much.